The universe's impossible objects. On August 14, 2019, gravitational wave detectors in Louisiana and Italy registered a signal, unlike anything they had ever recorded, a cosmic scream that had traveled for 900 million years to reach Earth. Within seconds, astrophysicists around the world realized they were witnessing something that shouldn't be possible. Two black holes, each more massive than our sun, had collided and merged in a cataclysmic explosion that released more energy in a fraction of a second than all the stars in the observable universe combined. But here is what kept scientists awake that night: the merged object that resulted had less mass than the two black holes that created it. 3 entire suns worth of matter had simply vanished, converted into pure gravitational energy that rippled through the fabric of space-time itself. This wasn't just strange. This was a violation of our most basic intuitions about reality, a glimpse into phenomena so extreme that the laws of physics, as we understand them, start to break down, and black holes are just the beginning. The universe is populated with objects so bizarre, so fundamentally alien to human experience, that even describing them in words feels inadequate. Neutron stars, where a teaspoon of matter weighs as much as Mount Everest. Magnetars with magnetic fields so powerful they could kill you from 1,000 miles away by disrupting the atoms in your body. White holes that might be spewing matter and energy from other universes or other times, and objects so strange we don't even have complete theories to explain them. This is the story of the universe's strangest objects, the impossible things that exist at the edges of physics, where reality becomes something we can calculate but can barely comprehend. Ask yourself this: if you could witness any cosmic phenomenon in the universe up close, protected by some impossible technology that kept you safe, which would terrify you most? And which would you choose to see? To understand why these objects are strange, we must first understand what normal means in cosmic terms. Our sun is a fairly typical star, a ball of hydrogen and helium undergoing nuclear fusion in its core, converting mass to energy according to Einstein's famous equation, producing the light and heat that makes life on Earth possible. The sun has been doing this for 4.5 billion years, and will continue for another 5 billion before it exhausts its fuel. It's massive, about 330,000 times the mass of Earth, but in cosmic terms, it's medium-sized, even small. The sun's core temperature is about 15 million degrees Celsius, hot enough that atoms cannot exist, only a plasma of naked nuclei and free electrons. The pressure at the core is about 250 billion times Earth's atmospheric pressure. These are extreme conditions by any human standard, yet they're completely normal for stars. Billions upon billions of stars throughout the universe operate under these same principles, fusing hydrogen into helium, radiating energy, maintaining a delicate balance between the inward crush of gravity and the outward pressure of nuclear fusion. This is baseline reality for the cosmos, already far beyond anything we experience on Earth. Yet this is what we consider normal. But when stars die, when the balance finally fails, reality goes completely off the rails. What happens next depends entirely on the star's mass. And this is where we enter the realm of the genuinely strange. When a star like our sun exhausts its hydrogen fuel, it begins fusing helium into carbon and oxygen in its core, while its outer layers expand dramatically, transforming into a red giant that could swallow the orbits of the inner planets. Eventually, these outer layers drift away into space, leaving behind the core a white dwarf. This is our sun's ultimate fate, and while it's dramatic, it's still within the bounds of what seems comprehensible. A white dwarf is roughly the size of Earth but contains about half the mass of the sun. Imagine compressing something 330,000 times more massive than our entire planet into a sphere the size of Earth. The density is staggering. A teaspoon of white dwarf matter would weigh about 15 tons on Earth. But here's where it gets strange. White dwarfs don't produce energy through fusion. They're not burning anything. They glow purely from residual heat, slowly cooling over billions of years. Like cosmic embers, the pressure inside is so extreme that electrons are crushed into a state called electron degeneracy. where quantum mechanical principles prevent them from being compressed further. This electron degeneracy pressure, not heat or fusion, is what prevents the white dwarf from collapsing entirely under its own gravity. White dwarfs exist in a quantum state that defies classical physics, the same principles that govern the behavior of electrons in atoms. Here on Earth, scaled up to astronomical proportions, are the only thing preventing these stellar remnants from collapsing into oblivion. Astronomer Subramanian Chandrasekhar calculated in the 1930s that there is a maximum mass for white dwarfs about 1 point for solar masses, now called the Chandrasekhar limit. If a white dwarf somehow accumulates more mass than this, perhaps by pulling material from a companion star and a binary system, electron degeneracy pressure can no longer support it. The star becomes unstable and detonates in a type E supernova, an explosion so bright it can briefly outshine an entire galaxy. These supernovae are so consistent in their brightness that astronomers use them as standard candles to measure cosmic distances, discoveries that revealed the universe as expansion is accelerating, a finding that earned the Nobel Prize and forced us to invent dark energy to explain it. But there is a stranger possibility with white dwarfs that physicist John Wheeler speculated about, and which remains theoretical. Could they crystallize? As white dwarfs cool over billions of years, the carbon and oxygen nuclei in their cores should eventually settle into a crystalline lattice structure. Essentially, the cores would become cosmic diamonds, spheres of crystallized carbon the size of Earth. Observations from the Gaia Space Telescope in 2019 provided the first evidence this might actually happen, detecting white dwarfs that appear to have paused in their cooling, releasing latent heat as their cores crystallize. If true, the universe is littered with diamond stars, objects made of crystallized carbon at densities and temperatures that boggle the mind. Ask yourself, what would it mean to stand on the surface of a diamond planet? If such a thing were possible, what would you see, feel, experience in such an impossible place? Yet as strange as white dwarfs are, they're comprehensible compared to what happens when more massive stars die. When a star between about 8 and 25 solar masses exhausts its fuel, the result is a core collapse supernova, an explosion that releases more energy in seconds than our sun will produce in its entire 10 billion year lifetime. The core that remains after this catastrophic explosion is something that shouldn't exist according to our everyday understanding of matter, a neutron star. Neutron stars are objects where the word extreme loses all meaning. Imagine taking the mass of our sun and compressing it into a sphere only about 12 miles across, roughly the size of a city. The density is approximately 1 billion tons per teaspoon. At these densities, atoms as we know them cannot exist. The electrons and protons are crushed together by gravity so intense that they merge into neutrons, creating a ball of nuclear matter, the same stuff that makes up atomic nuclei, but now forming an object the size of a mountain. The surface gravity of a neutron star is about 200 billion times stronger than Earth's. If you dropped an object from just 1 meter above the surface, it would hit the ground at millions of miles per hour, releasing energy equivalent to a large nuclear bomb. The gravitational pull is so intense that it distorts the light from the star, allowing you to see parts of the backside bent around the edges. You could literally see more than half the surface at once due to space-time curvature. But the truly mind-bending aspect of neutron stars is their interior structure, something physicists are still trying to fully understand. The outer crust, about 1 kilometer thick, consists of a lattice of iron nuclei embedded in a sea of electrons. Below that is the inner crust, where neutrons drip out of nuclei and form a superfluid, a quantum fluid with zero viscosity that can flow without friction forever. Deeper still is the outer core, consisting of superfluid neutrons, superconducting protons, and electrons. And at the very center, pressures become so extreme that we're not entirely sure what exists. Some theories predict quark matter, where neutrons break apart into their constituent quarks, creating a quark-gluon soup similar to what existed microseconds after the Big Bang. Other theories suggest even stranger possibilities: hyperons, strange matter, or states of matter we haven't even theorized yet. Astrophysicist Anna Watts has described neutron stars as the universe's natural laboratories for extreme physics, allowing us to test theories about matter and forces under conditions we could never recreate on Earth. But here's the truly unsettling part. Neutron stars spin. Most neutron stars rotate at hundreds of times per second due to conservation of angular momentum from the original star as rotation. As the star collapses, spinning slowly across thousands of miles, it speeds up dramatically when compressed to just 12 miles across like an ice skater, pulling their arms in. Some neutron stars, called pulsars, emit beams of radiation from their magnetic poles that sweep across spacelight. Lighthouse beams, the fastest known pulsar, PSRJ 1748-2446 rotates 716 times per second. At its equator, the surface is moving at about a quarter of the speed of light. The object is literally spinning so fast that relativistic effects become significant. Time passes measurably slower at the equator than at the poles, and the star bulges outward in a shape that defies Newtonian physics. Ask yourself, how can something made of matter with physical substance spin 700 times per second without flying apart? What force holds it together at such rotational speeds? The answer lies in neutron star material being the strongest substance possible in our universe. The nuclear forces binding neutrons together, combined with the intense gravity, create a material with a tensile strength billions of times greater than steel. Nothing stronger can exist without collapsing into a black hole. Neutron stars exist at the absolute edge of what's physically possible for matter. But there's a subset of neutron stars that take strangeness to an entirely new level: magnetars. These are neutron stars with magnetic fields 1,000 trillion times stronger than Earth, so powerful that the magnetic field energy dominates the object's behavior. Magnetar magnetic fields are the strongest force in the known universe apart from gravity itself. To put this in perspective, a magnetar's magnetic field at its surface is about 100 billion Tesla, the strongest magnetic field ever created by humans. For a tiny fraction of a second in a laboratory was about 1,000 Tesla, and that destroyed the equipment that created it. A magnetar's field is 100 million times stronger than that, sustained continuously. What does a magnetic field this strong do? It breaks physics as we normally understand it at around 1,000 Tesla. Quantum mechanical effects cause atoms to elongate into needle-like structures. At magnetar field strengths, atoms simply cannot exist in their normal form. The magnetic field polarizes the vacuum of space itself, affecting how light propagates through it. If you somehow got within 1,000 kilometers of a magnetar, the magnetic field would be strong enough to fatally disrupt the molecular bonds in your body. You would literally be ripped apart at the molecular level before gravity, or radiation could kill you. Even more bizarrely, magnetar magnetic fields are so strong that they create starquakes. The solid crust of the neutron star occasionally fractures and shifts due to magnetic stresses, releasing energy equivalent to thousands of supernovae in a burst of gamma rays. In 2000, for a magnetar called SGR 1806-20 located 50,000 light-years away, released a gamma-ray flare that affected Earth as ionosphere electromagnetic radiation from an object so distant that light from it took 50,000 years to reach us was still powerful enough to measurably impact our planet's atmosphere. Physicist Robert Duncan, who first proposed the existence of magnetars in the early 1990s, described them as objects where the magnetic field becomes the dominant force, overwhelming even the immense gravity and creating phenomena we're still struggling to fully understand. Only about 30 confirmed magnetars are known in our galaxy, but they might be responsible for mysterious fast radio bursts, brief, intense pulses of radio waves from distant galaxies that last only milliseconds, but release as much energy as the sun produces in days. If magnetars cause these bursts, and we're detecting them from billions of light years away, then the energy involved in producing them is almost incomprehensible. Yet even neutron stars and magnetars, as strange as they are, are objects made of matter, exotic matter under extreme conditions, but still matter obeying physical laws, even if those laws involve quantum mechanics and relativity. Black holes are something else entirely. They represent a place where our physical theories break down completely, where we can describe what happens using mathematics but cannot visualize or truly comprehend it. Black holes form when stars more massive than about 25 solar masses die, and their cores collapse. At this mass, nothing can stop the collapse, not electron degeneracy pressure. That supports white dwarfs, not neutron degeneracy pressure that creates neutron stars. The core collapses past the point of being matter in any meaningful sense, and continues collapsing until all its mass is concentrated at a point of infinite density, a singularity. Everything we understand about physics tells us this shouldn't be possible, yet the mathematics of general relativity, Einstein's theory of gravity, predicts it must happen. Around the singularity exists the event horizon, a boundary in spacetime where the escape velocity exceeds the speed of light. Nothing that crosses the event horizon can ever escape, not matter, not light, not information itself. This creates profound paradoxes that physicists still cannot resolve. Information in quantum mechanics is supposed to be conserved. You can scramble it, spread it out, but never destroy it. Yet anything falling into a black hole appears to be destroyed completely, violating this principle. Stephen Hawking spent decades grappling with this information paradox, eventually proposing that black holes slowly evaporate through quantum effects at their event horizons, radiation now called Hawking radiation. But this created new problems if black holes evaporate. Where does the information about everything that fell and go? Does it escape in the radiation? Is it encoded on the event horizon in some way? Or is it truly destroyed, forcing us to revise quantum mechanics? Hawking wrestled with this until his death in 2018, proposing various solutions without fully resolving the paradox. Physicist Leonard Susskind engaged in a famous debate with Hawking, proposing the holographic principle, the idea that all information about three-dimensional space can be encoded on a two-dimensional surface, like a hologram, applied to black holes. This suggests that everything that falls past the event horizon is somehow recorded on the horizon, as surface itself, preserved in a form we don't fully understand. This has led to suggestions that our entire universe might be holographic, that the three-dimensional reality we experience might be information encoded on a distant two-dimensional boundary. Black holes are forcing us to question the nature of reality itself. The interior of a black hole is literally unknowable. Nothing that goes in can come out to tell us what happened. Mathematically, we can solve Einstein's equations and describe what should occur. As you fall toward the singularity, tidal forces increase. The difference in gravitational pull between your head and feet becomes increasingly extreme until you race stretched into a stream of atoms, a process physicists gruesomely call spaghettification. Time dilates increasingly as you approach the singularity. From an outside observer's perspective, you appear to slow down and freeze at the event horizon, never quite crossing it, your image redshifting and fading. But from your perspective, you cross the horizon in finite time and continue falling toward the singularity we're all known. Physics breaks down. What happens at the singularity, where density becomes infinite and space-time curvature becomes infinite, is a question our theories cannot answer. General relativity breaks down, quantum mechanics breaks down, and we're left with mathematics that produces infinities and nonsense. This is why physicists are desperately seeking a theory of quantum gravity that would unify general relativity with quantum mechanics, and hopefully resolve what happens at the singularity. String theory, loop quantum gravity, and various other approaches all attempt this unification, but none has succeeded in producing testable predictions that would confirm or rule them out. Black holes represent the limits of our knowledge, places where reality does things we can describe mathematically, but cannot truly understand. Ask yourself, if you could somehow survive entering a black hole and could communicate what you experience back to the outside universe, which physics says is impossible. What do you think you would find at this singularity? What lies at the point where all our theories fail? But black holes get stranger still. Rotating black holes, called Kerr black holes after mathematician Roy Kerr, who first solved the relevant equations, have properties that seem to violate causality itself. A rotating black hole singularity is theoretically a ring rather than a point, and the mathematical solution suggests that if you could survive entering one, which you almost certainly couldn't, you might emerge in another region of spacetime, possibly another universe, possibly another time. These are the famous wormholes of science fiction, except the mathematics says they would be wildly unstable, collapsing before anything could traverse them. Some solutions even suggest closed time-like curves inside rotating black holes, paths through spacetime that loop back to their own past, allowing time travel. Most physicists believe these are mathematical artifacts that would be ruled out by a complete theory of quantum gravity, but we don't know for certain. Then there are supermassive black holes, monsters containing millions or billions of times the sun's mass, lurking at the centers of most galaxies, including our own Milky Way. Our galaxy's central black hole, Sagittarius asterisk, contains about 4 million solar masses. In April 2019, the Event Horizon Telescope collaboration released the first actual image of a black hole S shadow, the supermassive black hole at the center of the galaxy M87, containing 6.5 billion solar masses. The image showed a dark circle surrounded by a bright ring of glowing matter, falling in visual confirmation of something Einstein's equations predicted, but that seemed strange to actually exist. Physicist Katie Bouman led the computational imaging effort that turned radio telescope data from around the world into that iconic image, a feat requiring algorithms that could combine observations and compensate for Earth's atmospheric distortions. Supermassive black holes shape the evolution of entire galaxies. The material falling into them forms accretion disks that can outshine all the stars in a galaxy combined, creating quasars, the brightest persistent objects in the universe. Jets of particles accelerated to near light speed shoot out from the poles, extending for hundreds of thousands of light years. These jets can actually regulate star formation in their host galaxies by heating gas and preventing it from collapsing to form new stars. In a very real sense, supermassive black holes control the life cycles of galaxies, despite occupying a relatively tiny volume at their centers. How supermassive black holes formed in the first place remains an open question. The universe is only 13.8 billion years old, yet we've detected quasars powered by supermassive black holes that existed when the universe was less than 1 billion years old. How did these monsters grow so large so quickly? Standard models of black hole growth through accretion and mergers shouldn't produce them that fast. Some astronomers propose that primordial black holes formed directly from density fluctuations in the extremely early universe, providing seeds that grew rapidly. Others suggest intermediate mass black holes, hundreds or thousands of solar masses, formed from the first generation of stars and merged repeatedly. This remains an active area of research with no clear answer, but perhaps the strangest predicted black hole variant is one that has never been observed and might not exist: white holes. These are mathematical solutions to Einstein's equations that are essentially time-reversed black holes, where a black hole's event horizon only allows things to enter, never exit. A white hole's event horizon only allows things to exit, never enter. White holes would spontaneously spew out matter and energy, perhaps representing the other end of black holes or wormholes. Some speculative theories suggest the Big Bang itself might be explained as a white hole, the ultimate outflow of matter and energy from somewhere else. The complete lack of observational evidence for white holes leads most physicists to suspect they raise mathematical curiosities that do exist in our universe, but we can't rule them out entirely. The universe has surprised us before with objects we thought were impossible. Then there are quasi-stars, hypothetical objects from the early universe that might have briefly existed. A quasi-star would be a black hole surrounded by an enormous envelope of hot gas, larger than the orbit of Neptune but held together briefly by the black hole's gravity at its core. The black hole would feed on material from the envelope, releasing so much energy through accretion that it prevents the envelope from collapsing further. These objects might have existed for only a few million years brief by cosmic standards, but could explain how supermassive black holes formed so quickly in the early universe. If quasi-stars existed, they would have been the largest stars possible, not in mass necessarily, but in physical size, dwarfing anything in the modern universe. Another class of strange objects are boson stars, theoretical objects made not of ordinary matter but of boson's particles that can occupy the same quantum state. These would be held together not by nuclear forces or gravity alone, but by quantum effects. Boson stars are hypothetical, possibly explaining some dark matter. But if they exist, they would be bizarre objects, with properties unlike anything made of conventional matter. Some models suggest they could be transparent, invisible except for their gravitational effects, or can have exotic internal structures where quantum mechanics operates on macroscopic scales. Preon stars represent another speculative extreme hypothetical objects, where matter is compressed beyond even neutron stars, causing quarks themselves to break apart into smaller constituents, called preons. Preons are entirely hypothetical particles that might compose quarks and leptons. But if they exist, and if matter can be compressed sufficiently, preon stars might form. These would be even denser than neutron stars, existing at the absolute edge of what's possible before collapse into a black hole. Then there's the strange matter hypothesis, proposed by physicists like Edward Witten. Under extreme pressure, conventional atomic nuclei might convert into strange quark matter, containing strange quarks in addition to the up and down quarks found in normal matter. Strange matter might be absolutely stable, more stable than conventional atomic nuclei. This creates a terrifying scenario: a strange matter object. A strange star could theoretically convert any normal matter it touches into more strange matter through a chain reaction. If a piece of strange matter collided with Earth, it could theoretically convert our entire planet into a strange matter object in minutes. This is speculative, and most physicists doubt it's actually possible. But we can't rule it out with absolute certainty. Small strange matter objects, called strangelets, might exist in cosmic rays, or could theoretically have been produced in heavy ion collisions at particle accelerators. Extensive safety analysis concluded this risk is negligible, but it's a reminder of how strange the universe might actually be. Ask yourself, what does it mean that we live in a universe where such objects might exist? Where the fabric of reality permits neutron stars and black holes and possibly stranger things we haven't discovered yet? What does this tell us about the nature of existence itself? Gravitational waves themselves, ripples in spacetime caused by accelerating massive objects, represent another strange aspect of reality. Einstein predicted them in 1916, but thought they'd be too weak to ever detect. For decades, detecting gravitational waves was considered practically impossible. Then in 2015, the LIGO detectors achieved the impossible, detecting gravitational waves from the black holes colliding 1.3 billion light years away. The signal lasted only a fraction of a second, but it represented spacetime itself oscillating, stretching, and compressing by less than the width of an atomic nucleus. The detectors measured this impossibly tiny distortion in 4-kilometer-long laser interferometers, an achievement that earned the Nobel Prize. Since then, dozens of gravitational wave events have been detected: black hole mergers, neutron-star collisions, and hybrid events involving both. Each detection reveals something new about these extreme objects. The 2017 detection of two neutron stars colliding not only produced gravitational waves, but was observed electromagnetically across the spectrum, from gamma rays to radio waves. This confirmed that neutron-star mergers create heavy elements like gold and platinum through rapid neutron capture nucleosynthesis. The gold in your jewelry, the platinum in electronics, was forged in the collision of neutron stars billions of years ago, scattered into space by the explosion, eventually incorporated into the material that formed our solar system. We are literally made of and surrounded by debris from the universe's strangest objects. The discovery of gravitational waves opened a new way of observing the universe. Gravitational wave astronomy, allowing us to detect events that produce no light, that are invisible to conventional telescopes. Future detectors will be even more sensitive, possibly detecting gravitational waves from the Big Bang itself, revealing conditions in the first fractions of a second after the universe began. There are likely even stranger objects we haven't discovered yet. The universe constantly surprises us. Every time we develop new observational capabilities, we find phenomena we didn't predict. Fast radio bursts were completely unknown until 2007, and we still don't fully understand them. The first interstellar object detected passing through our solar system, Oumuamua, in 2017, exhibited properties unlike any comet or asteroid, accelerating in ways we couldn't fully explain with conventional outgassing. While most astronomers favor natural explanations, some have speculated it might be artificial, a probe or even a solar sail from another civilization. The second interstellar object, Comet Borisov, discovered in 2019, behaved more conventionally. But the fact that we are now detecting interstellar objects regularly suggests they are common. We simply hadn't been looking carefully enough before. Dark matter, which makes up about 85% of the matter in the universe, remains mysterious. We know it exists through gravitational effects on galaxies and galaxy clusters, but we don't know what it's made of. It could be exotic particles that interact only through gravity, or it could be massive compact halo objects like primordial black holes or brown dwarfs failed, stars too small to sustain fusion. If dark matter consists of primordial black holes, the universe could be filled with black holes ranging from asteroid size to thousands of solar masses, completely invisible except through gravitational lensing or the rare occasion when one collides with something. This would mean black holes far outnumber stars, that the universe's mass is dominated by these invisible gravitational traps scattered throughout space. Dark energy is even more mysterious, making up about 70% of the universe as total energy density and causing the universe's expansion to accelerate. We have no compelling explanation for what it is. It might be a cosmological constant, an intrinsic property of space itself, or it might be a dynamic field that changes over time. If dark energy's strength increases in the future, it could lead to a big rip scenario where accelerating expansion eventually tears apart galaxies, solar systems, planets, and eventually atoms themselves. Alternatively, if dark energy represents a false vacuum state, the universe could undergo vacuum decay, where a bubble of lower energy vacuum expands at light speed, completely rewriting the laws of physics everywhere it passes, effectively destroying the universe as we know it in an instant. This could happen at any moment or might never happen, we simply don't know. These are the ultimate strange objects, dark matter and dark energy, that compose 95% of the universe, but remain invisible and theoretical, known only through their effects. We are, in a very real sense, living in a universe where we don't know what most of it is made of. The matter we can see, stars, planets, gas, dust, everything made of protons, neutrons, and electrons represents only about 5% of the universe's content. The rest is dark, mysterious, fundamentally unknown despite being the dominant constituent of reality. Then there are theoretical objects from early universe cosmology. Cosmic strings, if they exist, would be one-dimensional defects in space-time left over from phase transitions. In the extremely early universe, thinner than an atom, but potentially stretching across the entire observable universe, each mile-long segment containing the mass of Mount Everest. Domain walls and monopoles are other predicted topological defects that might exist. Remnants of symmetry breaking in the first microseconds after the Big Bang. None have been observed, but they remain possibilities. Some theories predict the existence of bubble universes, regions of spacetime that underwent different symmetry breaking than our universe during cosmic inflation, creating pockets with different physical laws. These would be forever causally disconnected from us, moving away faster than light due to the expansion of space. But they might exist beyond our cosmic horizon. If eternal inflation is correct, bubble universes might be constantly forming, creating an infinite multiverse where every possible variation of physical laws exists somewhere. The strangest objects in the universe challenge not just our understanding of physics, but our philosophical intuitions about what can exist. They force us to accept that reality operates on principles that violate everyday experience. Matter can be compressed to infinite density. Magnetic fields can be strong enough to polarize vacuum. Objects can spin hundreds of times per second despite being made of nuclear matter. Spacetime itself can be torn, twisted, and made to vibrate. Information might be holographically encoded on surfaces rather than in volumes. Time might not flow uniformly. Causality might not be absolute. Ask yourself, does it disturb you or comfort you that the universe permits such extreme phenomena? What does it mean for our place in existence that we're made of ordinary matter, in an ordinary corner of space, while elsewhere reality does things that break our conceptual frameworks? Perhaps the most profound realization is that all these strange objects, white dwarfs, neutron stars, magnetars, black holes, and whatever else exists that we haven't discovered are created by the same physical laws that govern our everyday world. Gravity, electromagnetism, the strong and weak nuclear forces, quantum mechanics, these same principles that let you stand on Earth's surface and read these words also create objects. Where teaspoons of matter weigh billions of tons, where magnetic fields torture spacetime, where matter is crushed out of existence. There's no separate extreme physics that only applies to weird objects. It's all one set of laws operating under different conditions. This means the universe is fundamentally stranger than we intuitively grasp. The familiar world around us is just one expression of physical laws that permit even require extremes we can barely imagine. The search for these objects continues. New telescopes across the electromagnetic spectrum scan the skies continuously. Gravitational wave detectors are being upgraded to even greater sensitivity. Particle accelerators probe higher energies, potentially recreating conditions similar to neutron star cores or the early universe. Theoretical physicists develop new mathematical frameworks to describe extreme phenomena. Each discovery reveals the universe is more complex, more subtle, more fundamentally strange than previous theories suggested. What might we discover next? Primordial black holes from the early universe might be detected through gravitational lensing. Strange stars might be identified through their unusual properties. White holes might be observed if they exist. Naked singularities, black hole singularities without event horizons might be found, violating the cosmic censorship hypothesis that suggests all singularities should be hidden inside event horizons. If naked singularities exist, we could potentially observe regions where physics breaks down, where space-time curvature becomes infinite, where our theories make no predictions. This would be physics beyond physics, a phenomenon so extreme it can't be described by current theories. Or we might discover something nobody predicted, some object or phenomenon that requires entirely new physics to explain. This has happened repeatedly in astronomy. Before neutron stars were confirmed to exist through pulsar observations in 1967, many astronomers were skeptical such objects were possible despite theoretical predictions. Before black holes were detected through X-ray observations of binary systems and gravitational waves, many scientists doubted they actually existed in nature rather than just in mathematical equations. The universe has consistently proven stranger than even our most creative theories. Imagine. This creates both excitement and existential discomfort. We live in a universe we fundamentally don't fully understand, where the vast majority of its content remains mysterious, where the laws of physics permit phenomena that mock our intuitions and challenge our conceptual frameworks. the strangest objects in the universe, the neutron stars, magnetars, black holes, and whatever else lurks in the cosmic dark are reminders of how little we actually know, how vast reality is compared to our corner of it, how the universe operates on scales and principles that our brains, evolved to navigate terrestrial environments, struggle to fully grasp. Yet there's also profound beauty in this strangeness. The universe didn't have to be interesting. It could have been uniform, boring, predictable. Instead, it's filled with exotic objects and extreme phenomena. Laboratories where physics is pushed to its limits, where space-time bends and tears, where matter behaves in ways that seem impossible, but are mathematically inevitable given the right conditions. Every strange object we discover reveals something fundamental about how reality works, about the principles governing existence, about the possibilities embedded in the cosmic code that generates everything from quarks to galaxies, and we're capable of understanding them, at least mathematically, that 3 pounds of neural tissue and a chemical soup can derive. Equations describing black holes and neutron stars can calculate what happens at densities we can never directly experience, can predict gravitational waves, and then build machines sensitive enough to detect them. This is extraordinary. We are matter that has become conscious and turned its attention outward to understand the rest of matter, including the strangest examples of matter existence permits. We are the universe studying itself, discovering its own extremes, mapping its own possibilities. The strangest objects in the universe tell us that reality is richer, deeper, more varied than appearances suggest. They tell us that extreme conditions produce phenomena that challenge our categories and concepts. They tell us that gravity and quantum mechanics combined with sufficient mass or density or energy create objects that exist at the boundaries of what's possible, where small changes in conditions would create something even stranger or would cause collapse into something we can barely comprehend. They tell us we've barely begun exploring what exists in the cosmos, that new discoveries await in the data from next-generation telescopes and detectors, that the universe still holds secrets we haven't imagined, and perhaps most importantly, these strange objects tell us that we should expect surprises. The universe has never failed to surprise us when we've looked more carefully. Every new observational window, radio astronomy, X-ray astronomy, gamma-ray astronomy, neutrino astronomy, gravitational wave astronomy has revealed phenomena that were unknown or unexpected. The next window we open will undoubtedly do the same. Somewhere in the universe right now, something is happening that would revolutionize our understanding of physics if we could observe it. Some object is forming or colliding or radiating in ways we haven't theorized. Some exotic state of matter exists under conditions we haven't considered. Some phenomenon occurs that violates our expectations based on current theories. The strangest objects we know about: neutron stars with crustal mountains, magnetars with field lines that glow, with energy black holes that merge and ring like bells, white dwarfs crystallizing into diamond spheres. These are just what we've discovered so far in our first century of truly exploring the universe beyond visible light. What will the next century reveal? What objects lurk in data we haven't fully analyzed, in regions of space we haven't carefully observed, at energy scales or time scales we haven't examined? What awaits discovery in the cosmic dark? The universe is stranger than we know, stranger than we can know with current theories and instruments. But it's knowable in principle. The same laws operate everywhere. The same mathematics that describes falling apples also describes collapsing stars. We can understand these objects even if we cannot experience them directly, even if they exist under conditions that would destroy us instantly. This combination extreme phenomena that challenge intuition but obey mathematical laws we can decipher makes the strangest objects in the universe endlessly fascinating. They're real. They're out there. They're affecting the cosmos in profound ways, and we're discovering them, understanding them, incorporating them into our expanding picture of what reality includes. So look up at the night sky and remember, between the visible stars and the apparent emptiness of space, neutron stars, spin hundreds of times per second. Magnetars contort spacetime. With impossible magnetic fields, black holes lurk invisible and hungry in collapsing matter, releases energy that outshines galaxies. The universe is performing wonders and horrors on a constant basis, extremes that make our terrestrial experience seem impossibly tame and confined. We are living in a cosmos that contains the impossible, the mathematically necessary, but experientially incomprehensible, the fundamentally strange. And that strangeness, that cosmic weirdness operating according to deep principles we're still uncovering, is what makes existence far richer than any fiction could imagine. The strangest objects in the universe are real, and their existence proves reality is stranger, deeper, and more sublime than the human mind evolved to comprehend yet comprehend. We do step-by-step, discovery by discovery, expanding our understanding of what is, what can be, and what surely exists beyond the limits of our current knowledge, waiting in the dark between the stars for the next generation of explorers to find them, and marvel at what the universe has made possible through the simple operation of natural law, pushed to its extreme and beautiful limits.